a mass is dropped vertically and breaks up into two fragments when it reaches a height h. Now one fragment with a mass ma flies with a velocity of va directed west, and the other fragment flies east at vb, which is a different velocity. Now find the distance between the fragments when they hit the ground at the same time. So these fragments will undergo projectile motion and land at some distance x from the origin. So we'll take this as xa, and mass b lands at some distance xb from the origin. So noting there's no external forces acting on the system in the horizontal direction, then the center of mass of the entire system will not move horizontally. So after the system fragments and the masses land at those different positions, the center of mass remains at 0. And that's equal to minus xa by ma plus xb by mass b. So rearranging this equation, we can write xb as mass a on mass b multiplied by xa. So therefore the total distance between the masses being xa plus xb, which is equal to xa multiplied by 1 plus xb, which is ma on mb, by xa. And the correct answer is B. A system of particles is connected by rigid links, and we're asked to find the center of mass in the horizontal direction relative to the top particle. And each particle has a mass m, and the rigid links are massless. So the center of mass in the horizontal direction is minus L by m plus 3/4 L multiplied by m multiplied by the two masses, which has the same distance from the origin as per the question, and that's divided by 4 masses. So therefore we have minus 1 plus 6/4, or 3 on 2, which gives Lm on 2, and that's divided by 4m, or multiplied by 1 on 4m. So the center of mass is at L on 8 from this origin. So the correct answer is C. An explosive is detonated and it produces a triangular impulse on a particle with a mass m, which is initially at rest. Determine the average impulse and the compressed distance in the spring, which has a stiffness k, assuming no energy is dissipated. So by the impulse momentum theorem, we have the area under this curve is 1/2 by F0, being the initial force, by the duration of the impulse, is equal to the change in momentum of the particle, which is the mass by the velocity, given the initial velocity is 0. So from this, we obtain V is F0 by the duration on 2m. And now we can apply the conservation of energy. We have the kinetic energy of the mass, which is 1/2 by m by v squared, which is f naught squared td squared on 4m squared, and that's transferred into elastic potential energy when this spring is compressed over some distance x. So solving for x, so we end up with f naught by td over the square root of 4 km, which is 2 root km. And note that the average impulse is the average force, which is f naught plus 0.12 multiplied by the duration. So the correct answer is E. A ball has an initial velocity of 2 meters per second, and it collides with another ball initially at rest. So this is a glancing collision. Determine the final speeds of both balls at the instant after impact, and assume a perfectly elastic collision with both balls having the same mass m. So applying a conservation of momentum in the horizontal direction, we have the initial momentum being the mass by the velocity is equal to the final momentum in the horizontal direction. So we have mv1 cosine 50 degrees plus mv2 by cosine 40 degrees. And a conservation of momentum in the vertical direction gives 0 for the initial momentum, and that's equal to mv1 by sine 50 degrees minus mv2 by sine 40 degrees. So from the second equation, we can solve for v2, which is equal to 1.192 v1. And if you substitute v2 into the first equation, we'll be able to solve for v1, which is 1.29 meters per second. And then if you substitute this into this equation, we'd get v2, which is 1.53 meters per second. So the correct answer is A. A man stands on the left end of a stationary barge that's floating in still water. And the mass of the man is m, and the barge has a mass of capital M. Now if the man starts to walk at a velocity v east, what is the speed of the barge? And we're told to ignore contact forces between the barge and the water. So the initial momentum is 0 because the barge is stationary and the man is stationary. And the final momentum of the system is the mass of the man by the velocity. And because there's no external forces acting on this system in the horizontal direction, if the man walks to the right at some velocity, then the barge must move to the left at some velocity, such that the momentum of the system is conserved. So therefore the speed of the barge is m on m by v. So the correct answer is A. The density function and length of a bar are given below. Find the center of mass relative to the left end of the bar. So that's equal to the integral of the distance to some element of the bar, which has an infinitesimal thickness dx. So we have x by the density function, which is 1/2 by x squared plus x And given this is a linear density function, we integrate over x. And we're integrating from x equals 0 to 1 meter. And that's divided by the total mass of the bar. So we have the integral from x equals 0 to 1 meter of the density function, which is 1/2 x squared plus x, integrated over x. So if we evaluate the top integral from x equals 0 to 1, we have x to the 4 on 8, so we get 1/8, plus x cubed on 3, which gives 1/3, and that's divided by x cubed on 6, so we get 1/6, plus x squared on 2, which gives 1/2. So calculating this out gives 0.7 meters, and the correct answer is D. A ball has an initial velocity v0. It collides with another ball initially at rest. Which of the following relationships show that energy was conserved where the collision is elastic? Well, the initial kinetic energy of the system is 1/2 by mv0 squared, and that's equal to the final kinetic energy of the system, which is 1/2 by the mass of the ball by the speed squared, plus 1/2 by the mass of the other ball by the speed squared. So if we do some cancellations, we get v0 squared is v1 squared plus v2 squared, and the correct answer is B. A bullet with a mass of 2 grams is launched into a block at an initial speed v0. Find the initial speed of the bullet if the block swings to a height of 0.5 meters. And we'll assume that the bullet is lodged into the block, meaning it's a perfectly inelastic collision. So applying the conservation of momentum, we have the mass of the bullet by the initial velocity is equal to the final momentum when the bullet's lodged into the block. So we have the mass of the bullet plus the mass of the block or crate multiplied by the final velocity of the system. And therefore the initial kinetic energy of the system is 1/2 by mb plus mc by the square of v dash, and that's converted into gravitational potential energy. So we have the mass of the block plus the mass of the crate by the gravitational acceleration by the height h. So therefore we can solve for v dash, which is √2gh. So substituting the numbers given in the problem and a gravitational acceleration of 10 meters per second squared, we get v dash is 3.162 meters per second. And then we can substitute this into this equation to solve for the initial speed of the bullet. So the mass of the bullet is 2 grams or 0.002 kilos, and we're given the mass of the crate, and we know v dash, so we can solve for v0. So that gives around 794 meters per second. So the correct answer is D. If the net force on an object is 0, which of the following is true? So A is false because the object is not accelerating. There are no forces acting on the object, which is also false because there can be forces acting on the object that cancel each other out. And the linear momentum of the object is constant. So this is true because the force is the change in linear momentum. So the correct answer is C. And the object's speed is not necessarily constant if the mass is not constant. And the object's not necessarily in static equilibrium. So it can be in dynamic equilibrium if the velocity is constant. A bullet with a mass mb is launched into a block with a mass mc at an initial speed of v0. Find the dissipated energy in a collision and assume the bullet's lodged into the block, so we have a perfectly inelastic collision. So the initial momentum of the system is due to the bullet being the mass of the bullet by the velocity, and that's equal to the mass of the bullet plus the mass of the crate being the mass of the system by the final velocity of the system. And applying a conservation of energy, we have the kinetic energy of the bullet being 1/2 by the mass of the bullet by the square of the initial speed minus the dissipated energy when the bullet's lodged into the block, so due to the breaking of bonds, and that's equal to the final kinetic energy of the system, which is 1/2 by the mass of the bullet plus the mass of the crate by v dash squared. So we have mb squared by v0 squared on mb plus mc all squared. So solving for the dissipated energy, we have 1/2 by the mass of the bullet by the initial speed squared, which will factor out. And then subtracting this expression, we have mb by mb v0 squared over mb plus mc. So the correct answer is B. Now that you've covered the first quiz, we'll revise the main topics in the systems of particles and linear momentum unit. So be familiar with the center of mass of discrete bodies and continuous bodies using the integral, where you may have a linear density function for bodies that don't have a uniform density. And know the difference between center of gravity and center of mass. So here, for example, if we have a planet and a small object near the planet, then the center of gravity will be equivalent to the center of mass. But if the object has a significant size compared to the planet, then the gravitational force will be distributed non-uniformly on the object. So in this case, the gravitational force will be stronger near the origin, and the center of gravity will be to the left of the center of mass of the bar, which is in the middle for a bar with a uniform density. So noting the gravitational acceleration and the gravitational force is inversely proportional to the radial distance between two masses. And also be familiar with the linear motion of a system of particles. So if we take m as the total mass of the system of discrete particles and multiply it by the position of the center of mass, we get the sum of the distances by the mass of the particles from the selected origin. And if we differentiate this equation, we get the mass by the velocity of the center of mass is equal to the sum of the momenta of the individual particles, and differentiating again, we get the mass by the acceleration of the center of mass is equal to the sum of the mass by the acceleration of each particle, and that's equal to the net external force acting on this system of particles. So we can visualize the net force as the change in momentum of the center of mass. In other words, if the net external force on a system of particles is 0, and the center of mass was initially at rest, then the momentum of the system will be conserved, and the center of mass will not move. And be familiar with what an impulse is, which is a force applied over a short period of time. So if we integrate the force over the time, we get the area under the force time curve, and that's one way we can define the impulse. And using the mean value theorem for integrals, you can also define the impulse as the average force multiplied by the time interval over which it's applied. And this leads to the impulse momentum theorem, where the impulse is equal to the change of momentum, in this case of a particle. So that's equal to the final momentum minus the initial momentum of the particle, assuming the particle's mass does not change. And for a system of particles, we can apply the conservation of momentum where there's no net external force acting on a system of particles. So momentum will not be conserved for an individual particle, because when this interacts with another particle, it'll have an impulse applied to it. But momentum is conserved for the system of particles. So when we look at a pair of particles, the impulse due to the contact between the two particles cancels by Newton's third law. So momentum is not conserved only if there's a net external force on the system, in the direction where we're applying the conservation of momentum, given momentum as a vector quantity. And with elastic collisions, no energy is dissipated and energy is conserved, such as the collision between billiard balls, which can be treated as elastic. And for an inelastic collision, such as a bullet getting lodged in a block where bonds are broken, then energy is dissipated and the energy of the system is not conserved. And with these concepts in mind, we'll move on to the next quiz. Two particles each with a mass m are moving horizontally and vertically as shown. And if their collision is perfectly inelastic, find the angle of the velocity vector after the collision. So applying a conservation of momentum in the horizontal direction, we have the mass by velocity 1 is equal to the mass of both particles, which stick together after a perfectly inelastic collision and move off at some velocity. And in the horizontal direction, we have v cosine theta. And applying a conservation of momentum in the vertical direction, assuming these particles are on a horizontal tabletop, for example, so the gravitational force is acting out of the plane, we have the initial momentum is equal to the final momentum in the vertical direction, which is 2mv sine theta. And then dividing these two equations together, we have sine theta on cosine theta, which is tan theta, and that's equal to v2 on v1, and therefore the angle theta is the arctan of v2 on v1, so D is the correct answer. A man with a mass m stands on the left of a stationary canoe, which has a mass m and length L. And this canoe is floating in still water, so it's at rest. Now if the man walks at an average velocity of v east to the end of the canoe, how far will the canoe move and what is its average velocity? And we can ignore contact forces between the canoe and water. So we know the center of mass of the canoe does not move because the system, being the person and the barge, is not subjected to any horizontal external force, given we're ignoring contact forces between the canoe and water. So the center of mass relative to the origin is the mass of the person by 0 plus the mass of the canoe by the length on 2, assuming the canoe has a uniform mass density. So that distance is L on 2 from the origin. And this here is the center of mass. So to get the center of mass, we just divide ml on 2 by the mass of the person plus the mass of the canoe. So now if the person walks to the other side of the canoe, this canoe will move to the left by some distance d, because this center of mass will not move. So if we compute the center of mass of the system relative to the same origin, so this distance the canoe has moved is equal to d, we have the center of mass in this case relative to the origin is the mass of the man by the length of the canoe minus d plus the mass of the canoe by the length on 2 minus d. And dividing by the total mass of the system, we have the mass of the person plus the mass of the canoe. So given the center of mass will not move, it has the same distance to the origin. So we can equate these two expressions while cancelling out the denominator. So we get ml on 2 is m by L minus d plus m by L on 2 minus d. So we can cancel out ml on 2 and solve for d, and therefore d is equal to ml on m plus m. So the correct answer is either b or d. Now given the person moved at an average velocity v to the right of the canoe, that's equal to the length of the canoe on the time taken, and therefore the time taken is equal to L on v. And the average velocity of the canoe is the distance travelled, which we've determined here, and the distance travelled by the canoe is done over the same time that the person moves from one end to the other. So we have d on t or dv on L. So we get mlv on L or mv on m plus m, which is the average velocity of the canoe. And therefore the correct answer is B. A system of particles is connected by rigid links. Find the center of mass in the y direction relative to the top particle. And each particle has a mass m, and the rigid links are massless. So we have y of the center of mass is minus L on 3 multiplied by m multiplied by these two particles, and we have minus L on 3 plus 4L on 5 multiplied by the mass of the third particle, and that's divided by the mass of all four particles. So we get minus 2ml on 3 minus 5L plus 12, which is 17L. So we have 17ml on 15, and that's divided by 4m. So we have minus 10 minus 17, which is minus 27, on 15 by 4 is 60, which is equal to minus 9L on 20. So the correct answer is A. A variable force acts on a particle of mass m, which is initially at rest. What is the velocity of the particle? Well, here we can use the impulse momentum theorem, where the impulse is the area under this graph. So we have the area of the trapezium is 1 second plus 3 seconds on 2 multiply by 10 newtons. And that's equal to the change in momentum of the particle. So we have m by the velocity, given it's initially at rest. So note that the impulse is in Newton seconds. And if we solve for the velocity, we get 20 on m, Newton seconds per kilo. And recall that 1 Newton is 1 kilo meters per second squared. So the answer will also be in meters per second. But d is not divided by m, so the correct answer is C. We have two masses that are hanging off a meter stick, with one mass being 5 kilograms at the far left point, and one of the masses is 1 kilogram hanging from the far right point. And the meter stick is supported at its midpoint. So this distance here is half a meter. How far from mass 2 on the right hand side should a third mass be placed to balance the meter stick? So taking our origin at mass 2, we have 1 meter by 5 kilograms plus 0 meters by 1 kilogram plus the unknown distance of mass 3 by 8 kilograms on a total mass being 5 kilos plus 1 kilo plus 8 kilograms is equal to 0.5 meters from the origin, where the meter stick is balanced. So what we have is 5 plus 8d equals 0.5 by 14, which is 7, which implies d is 2 on 8 or 1 on 4 or 0.25 meters, which is 25 centimeters, so the correct answer is B. A car with a mass of 1 ton, which is travelling east at 30 meters per second, has a head-on collision with a bus travelling west at 25 meters per second. What is the work done by the friction force from after the crash until the vehicle skid to a stop, assuming a perfectly inelastic collision? So after the collision, the car and bus stick together and move off at the same velocity. And this velocity is obtained using a conservation of momentum. So we have the mass of the car by the velocity of the car plus the mass of the bus by the velocity of the bus, which will give a momentum vector pointing in the opposite direction. And that's equal to the mass of the car plus the mass of the bus by the velocity of the system. So if we substitute for the masses and velocities that are given, we'd get V dash, which is minus 20.417 meters per second. So V dash points to the left or west. And remember, the friction force acts in the opposite direction of motion, and we can find the work done by the friction force using the work kinetic energy theorem. So the final kinetic energy when the system comes to a stop is 0 minus the initial kinetic energy, which is 1/2 by the mass of the car plus the mass of the bus by the speed squared. So if you make those substitutions, we get the work done by the friction force, which is minus 2501 times 10 to the 3 joules, or 2501 kilojoules. So the correct answer is A. The density function and length of a bar are given below, and a particle with a mass of 1/3 of a kilo is attached to one end of the bar using a rigid massless link. Find the center of mass relative to the left end of the bar. So the center of mass is the integral over the length of the bar, and we integrate x by the linear density, which is 1/2 x squared plus x over x, and plus the mass of the particle by 0. And that's divided by the mass of the particle plus the mass of the bar, which is the integral over the length of the bar, and we integrate the linear density function, which is 1/2 x squared plus x over x. So therefore we can obtain a center of mass as x to the 4 on 8, which will give 1/8, plus x cubed on 3, which will give 1/3, on 1/3, plus, and the integral evaluates to x cubed on 6, or 1/6, plus x squared on 2, which will give 1/2. So that gives a center of mass of 0.46 meters. So the correct answer is A. A 2 kilo particle moving at a velocity of 2 meters per second east towards a 4 kilo particle, which is 2 meters away, which is moving at 3 meters per second west. Assuming the particles undergo a perfectly inelastic collision, find the time taken for the particles to return to one of the starting positions. Well, the position of the first particle relative to the origin that we choose, which we'll call particle A, is the initial position plus the initial velocity by time t. And particle B has a position xb, which is equal to the initial position at 2 meters minus the velocity by time. So when these particles collide, xa is equal to xb, which means that 2t is equal to 2 minus 3t, and therefore t is equal to 2 on 5, or 0.4 seconds. And if you substitute t into one of these equations, you get the position of the collision, which is at 0.8 meters. Now, using the conservation of momentum, we have the mass of particle A by the velocity minus the momentum of particle B, which is in the opposite direction. So we have 4 kilograms by 3 meters per second, and that's equal to the final momentum of the system, which is 2 kilograms plus 4 kilograms by V dash. So that gives V dash is minus 1.3 meters per second. So the particles move off at a velocity to the left, towards the starting position of particle A. So we have the final position at the origin is the initial position at the collision minus V dash by time t dash. And solving for t dash, the particles take 0.6 seconds to return to the origin. So the correct answer is C. A ball with a mass m is travelling horizontally with a velocity v, and it strikes a wall and rebounds along its initial direction at the same speed. What is the magnitude of the impulse delivered to the ball? Well, the impulse is the change in linear momentum of the particle. So the final momentum is minus mv minus the initial momentum, which is mv, so that gives minus 2mv. And therefore the magnitude of the impulse, which is a vector, is 2mv. And the correct answer is B. A particle with a mass ma is travelling at an initial speed v0 and has a glancing collision with another particle with a mass mb. Which of the following statements is necessarily true? So we can rule out C and D because we're not told specifically that the collision is elastic or inelastic. And if we do a conservation of momentum in the vertical direction, we have the initial momentum of the system in the vertical direction is equal to the final momentum. So we have mass A by velocity A sine theta A minus mass B by velocity B by sine theta B. So therefore, for momentum to be conserved, if the magnitude of momentum of particle A is larger than that of B, then a deflected angle A must be smaller than that of B. And this is seen if you put MAVA sine theta A on the left hand side of the equation. So we get MBVB by sine theta B. So the correct answer is E.